Assalamu alaikum. Bismillahirrahmanirrahim. In the previous class, we are discussing the AC. We have introduced the AC to AC converters, which is called as AC to AC controllers in this book. We are discussing a single phase full wave controller with a resistive load. Actually, if we see the circuit diagram, this is the circuit diagram for single phase full wave controller. Since it's a full wave, we use two thyristor T1 and T2, and since thyristor is a unidirectional device, we need two thyristors. For the positive half cycle T1 conducts and for the negative half cycle T2 conducts, and the gate pulses for both the thyristors are spaced at 180 degree from each other. You can see that we decided we will give a delay of alpha to one of the pulse, which trigger the T1, and the next pulse for the T2 will come after pi plus alpha, as it is suggested. This is the input waveform of the source voltage over here with the V maximum, and this is the output over here. We decided to fire the angle at alpha. After that, we have this kind of situation. Your output voltage is like that, and your current waveform always follow the input voltage because it's a resistive load. And if your source voltage is given by under 2 Vs sine omega t, because it always follow sinusoidal shape, and the delay angles are given by of T1 and T2 are equal, and alpha 2 is equal to pi plus alpha. The RMS output voltage can be found. And you know that during it's very tricky to write down this equation, and since it's a RMS output, root mean square, this is the root, 1 over 2 is the root, mean is this integral, and square is the waveform for this input. You know that the input is like that, and under 2V, that is square, and 2Vs square sine square omega t d omega t. And this 2 comes from, it's a very interesting, since this we are interested in an area under the curve, and our active area is from alpha to pi, and since it's squared, then this effects are also this is also become positive, it goes to the upper side. And since in a single cycle we have two this kind of shapes, this 2 comes from here, since we have this and this, and but we consider only the one shape, this one, and apply everything over here and just multiply it by 2. 1 over 2 pi is the total period. Actually, this is the root mean, this is the mean, okay, and from alpha to pi. And if we try to solve it, since it's a scale and scale, we need to convert it into a half angular identity. You already know this process, and if you open up the integral, then you left with this equation. And this mathematical process is in depth. I hope you can do it by yourself. It's not a big deal. Now, by varying alpha from 0 to pi, the output alpha is equal to pi, the output can be used from Vs to 0. If it is pi, then we don't have anything over here, and if it is 0, let's put it 0 over here, alpha 0 here, alpha 0 here. This part becomes 0, this one. Pi cancel pi, and output is the source voltage. It's very easy, and you can verify your results by just applying a simple this limit principle. Look at the figure. The gating circuit for the thyristor T1 and T2 must be isolate. It is possible to have a common cathode for T1 and T2 by adding two diodes, as shown in figure 11.3. Like that. What it will say? It says this kind of configuration. If it's a positive pulse, it will go this way. Okay, pretty interesting. And negative pulse, it will take this way. It's a common single phase full wave controller is common cathode. But it does say because the circuit have a common terminal for getting the signal of T1 and T2, only one isolation circuit is required, but at the expense of the power. So, due to two powered devices conducting at the same time, the conduction loss would increase and efficiency would be reduced. Now, know that there are two devices, two diodes conducting, one thyristor, one diode conducting at the same time. We did this to provide the isolation. There is another way to implement this kind of situation. They have a common cathode. Yeah, this is the cathode, this is the anode. So we get the gating signal. We need only one gating signal to control the thyristors. Second part is a single phase full wave controller can also be implemented with one thyristor and four diodes. That is also pretty interesting. We need only one thyristor. In this case, the four diodes act as a bridge. Look at the diagram. Okay. And the voltage across thyristor T1 and its current are always unidirectional. With a resistive load, the thyristor current would fall to zero due to natural commutation in every half cycle. What will happen? There is possibility you use IGBT or thyristor during a positive half cycle. It will be conducted like this. From D1, P1 and D2 and go to the load during the negative half cycle D4, T1, T3 and go to the load. However, the current through the load is only unidirectional, and with resistive load it's pretty interesting, and we are going through this one. thyristor will be automatically off at this point. Thyristor current would fall to zero due to natural completion in every half cycle. However, if there is large inductance involved in the circuit, the thyristor may not be turned off in every half cycle, and we have a loss of control. It requires another additional zero crossing detector circuit to guarantee the turn off process of the thyristor for the next firing angle. Three power devices conduct at the same time, then efficiency is also reduced. Two diodes, one thyristor, they conduct at the same time. We have a losses. Bridge rectifier and thyristor act as a bidirectional switch, and this is available in your single package. So we have gone through this pretty interesting single phase controller. And controller is excellent control over the AC signal. So what is the gating signal? Generate a pulse signal at zero crossing of the supply. If being an electrical engineer, it's very easy. You can find certain zero crossing detectors or a very simple circuitry which can produce a pulse at the zero crossing of your input supply. Delay the pulse by a desired angle for getting through the gate isolated circuitry. Yes, there are certain mechanisms or very small circuit parts which can be introduced in the circuit to delay your pulse, and you need another pulse which is displaced by the pi from the initial pulse. If you look at the diagram very carefully, this is your input supply, and this one is the current, load current, and more R. We start firing at delta, and we have a same shape as the current always follows shape of the input supply. Then again it is fired at the same angle plus pi, and we are getting sequence thyristor T1, which is interesting. Now we have discussed three sound circuits, so we one by one. This one is simple back-to-back two thyristor, one operating at one time, extremely efficient. This is the second circuit with a common cathode with a single control circuit. Two thyristor connected in opposite direction. The two diodes connected back to back in the opposite way. And this is the third part where the bridge, diode bridge is used with the thyristor connected in between. Now let's see the performance parameter for this circuit. It's also pretty interesting, but you need to be very keen or attentive during this whole process of the circuit. Understanding is important. Finding the performance parameter of single phase full wave controller. As name suggests, a single phase full wave AC controller has a resistive load, okay, with the input supply 120 volts with the frequency 60 Hz. And we decide to get triangle 5 by 2. Determine the RMS output voltage and the input power factor, average current of the thyristor and RMS current of the thyristor. Actually, RMS output is that will determine your performance. Along with these average currents and the RMS currents. The given things we have it. The next is we have RMS value at the from the supply we can get the maximum value. Filing is 5 by 2. We can get the output RMS from the equation 11.1, that is V naught 120. Okay. Now your alpha is 5 by 2. It is 5 by 2. You can it is 5 by 2, this factor is 0, then we left with the 5 by 2. And we left with the 1 over under 2 from here. Okay. And that is 1 over under 2 into your source voltage. That is 24.85. The RMS load current is given by V naught over R, and the load power is given by I square R. Because the input current is the same as the load current, we already see this is pretty important. Input current is the same as the load current. Emitting current and the leaving currents are same in all the circuits. Similarly, entering current and leaving current same. This very basic circuit is same. Entering and leaving current are the same. It will make our life easier. Because the input current is the same, the input pole ampere ratings are. You know that EA is VSIS, VS is I naught, same. This is the rating, and the input power factor is given by P naught over VA. P naught we have already, this is the load side, VA the source side. And we already know this equation and the firing angles, and it is 0.707. This equation, power factor equation, V naught over Vs, it comes from here, V naught over Vs. This is the equation. Yeah. Now the average thyristor current can be found by this formula. It's alpha, this is 5 by 2 to 5, and this is the inherent property which we already seen. And we need average thyristor current under 2 Vs, that's the maximum. We need to put it over here. And just evaluate this. Apply the limits. We have a average thyristor currents. And and the RMS value of the thyristor current is the same. This is just the average value. Okay, you know that how we can calculate the average of a class. Sum of the marks obtained by the student and divided by the number of students. Here is the same. Since it's a current, we need the voltage divided by the resistance, and the average voltage can be computed by the average, the range, and the total range of voltage. This is the scenario. The RMS value of the thyristor current is the same. We need to just scale them up. This is a scale, this is a scale, and since it's a scale, it cannot be solved in the integral. We need to refer it to the half angle identities or double angle, whatever it is called. Open up everything, remove the things from the integral, simplify it. We have this kind of scenario. Now, since we already told about the limit of the circuit, that is starting from pi/2, and you are plugging everything over here, you have answer. I think these things are clear to you. The key points are just the output of this controller contains no DC components because it's a AC to AC converter, and you can see the relationship from, or you can see the output of the controller. It doesn't have any DC part, and you can vary the delay angle from 0 to pi, and so does the RMS value changing from Vs to 0. Okay, so this is very interesting. It doesn't have any DC component. Now, single phase full wave controller with inductive load. We won't go into the detail of this controller. With the inductive load, we will see the waveform only. It's pretty interesting. You can see that you apply a gate pulse for thyristor T1, apply a gate pulse to thyristor T2. What happened actually? You know that due to the highly current inductive coils in the circuit, what will happen? You will delay by a certain angle with respect to the voltage. This is the same situation. Your voltage is done or blocked after the pi, but current is still conducting because of this inductive load. Inductors are energized, and you need to, and when during the natural commutation process, when your wave is clipped over here, what will happen? The energy stored in the inductor keeps supplying your load. Like you see. Maybe you can skip this part. You need to have the understanding of this waveform only. We won't go to the detail of this inductive load anymore. The understanding is more important. questions or anything you can ask. And this is all about our topic today. And in the next lecture, we will discuss the three-phase AC to AC converter. As far as I know, I think you can go through the lecture and understand it very